Good evening, one and all. I welcome you to the sixth live session of the NPTEL course, Oil Hydraulics and Pneumatics. The course tutor for this particular course is Professor Somshekhar Siramat from the Department of Mechanical Engineering, IIT Madras, and I am the teaching assistant. I am Arnav. I hope that you have gone through the uh, video lectures for the previous weeks and you have attempted the assignments. So today we will be discussing a few questions pertaining to week 5 mostly, where we will be dealing with different types of valves like flow control valves and pressure control valves, and we'll be discussing a few circuits, hydraulic or pneumatic circuits. Okay, so let's start today's session. So the first question. Which of the following statements correspond to a bleed off circuit? So, as we know that uh, bleed off circuit it comprises of a flow control valve that bleeds off the uh, oil supply either from the main line or from the return line, depending on how you want to control the speed of the actuator. So, it is an alternative to the meter in and the meter out circuits. So the question asks which of the following are correct. It generates less heat and can be more economical than meter in or meter out circuit. So this is true because you are not directly causing a pressure drop along the system line. What you are doing, as you can see in this particular figure, you are bypassing the flow from the main line to the tank through this flow control valve. So suppose you want to allow, suppose the pump is discharging around 100 liters per minute flow, say, and you want uh, the flow to this particular cylinder to be around 90 liters per minute. So what you need to do is you need to bypass 10 liters per minute flow through this particular flow control valve, and it is adjustable type, so this value can be adjusted and accordingly you can control the speed of this actuator. So this is for controlling the returns, the speed in the this is during the return stroke. If it is connected to this line, then you can control the forward stroke. Like if you actuate this S1. So it's much simpler than your meter in or the meter out circuits, wherein we directly put the flow control valves here or here. So yeah, it generates less heat, and it can be more economical. That is true. It can precisely meter flow to the tank even when leakage to the components is present. This is not correct because the main disadvantage is here is the leakage. So and the precision that is that comes up, the precision issues that comes up due to this leakage. So from this flow control valve, there can be some leakage happening, and instead of this 10 liters per minute that I showed that bleeds off, it can be say around 12 liters per minute. This extra 2 lpm that I am writing, that is the leakage, say. So what the remaining flow that goes into the circuit, it's basically 88 liters per minute. I'm just writing these numbers. This is not exact, or it's just a figurative. So we wanted flow of 90 liters per minute corresponding to a given piston velocity, say. Uh, so what we are actually getting is 88 liters per minute due to this extra leakage. So you can understand that this is not precise due to this leakage. So the option B asks it can precisely meter flow to the tank even when leakage through the components is present. So this is not correct. It is not precise. It can be used when the actuator load is dynamic. Again, this type of bleed out circuit, bleed off circuits, it can't be used against dynamic loading conditions. That is, when the load on this particular cylinder that is not a static or it is not constant, then the pressure that is acting in the circuit will be not constant, it will be dynamic. So as a result, what happens? The pressure drop across this flow control valve, it will change. This particular pressure drop will change because here it's atmospheric pressure, say, and here the pressure is changing due to the dynamic load. As a result, the flow through the bleed off circuit, and that also is not compensated, and hence it's not constant. So we will not get a constant flow in this line since this is varying. So it can't be used. This is not the correct option. It directly controls the speed of the actuator. As you can see that here the speed of the actuator is not directly controlled by this flow control valve. It is indirectly controlled. Why? Because the bleed off circuit is simply bleeding off the hydraulic oil at controlled amounts, at controlled discharge, and hence it is indirectly sending the remaining amount of liquid into the actuator through the direction control valve. So you can understand that it is not a direct operation, it is an indirect operation. So it indirectly controls the speed of the actuator. So only the first option is correct. So I think you could understand this. If you just look at the other figure here, what is the difference between this one and this one? This is when we are when the flow is happening into the cylinder. That flow you are controlling through this bleed off circuit. So let me just write this as Q in. So this the value of Q in is controlled by this particular bleed off circuit. It is quite like the meter in circuit. Whereas here you can see that you are controlling the Q out. That is the amount of oil that is flowing out of the actuator during the return stroke. Again, if I had said that it is during the forward stroke, then this would be completely reverse. Okay, so yeah, going on to the next question. The discharge through an orifice depends on which of the following factors: the cross sectional of the orifice, the shape and length of the restricted section, the pressure difference across the orifice, and fluid viscosity. So as we know that flow control valve basically works on the principle of a restricted section, a flow through a restricted section or an orifice. So this is a fixed cross section orifice. So flow is coming in from here, it is getting restricted, and you have an outflow here. So this restriction is controlled to control the flow, the discharge through this circuit. So if you are asked that what is the value of Q through this particular orifice, or through this particular circuit, then that depends on the cross section, this area. It depends on the shape and length of the restricted section. This length and shape. And the shape means this particular shape. It can be like this. It can be like this. There are different shapes. So depending on that, your coefficient of discharge will be varying. And pressure difference across the orifice. Yes, that affects the flow, because the flow happens from a region of higher pressure to a region of lower pressure here, and hence the pressure difference that is acting. This is basically the difference between the upstream and the downstream pressure across the orifice. And the fluid viscosity. Yes, because if the fluid is thick, it is more viscous, then there will be more resistance to the flow. So apart from this delta P, if we just look at this section, a thick fluid needs to flow through this small section. It will its discharge will be less. If a relatively less viscous fluid tries to flow through this section, the resistance will be less and the discharge will be more. So this also plays a governing role. So if you look at the mathematical relationship, the discharge through an orifice varies with the differential pressure, that is delta P, across the orifice that I showed here in the following manner. So I hope that you're acquainted with this. Q square is directly proportional to delta P. So the flow through this orifice is directly proportional to the square root of the pressure drop across the orifice. Okay. So yeah, this option is correct. It is not independent of delta P. It is dependent on delta P. It is dependent by following this relationship. So if you look at the curve, Q versus delta P curve, which is one of the characteristic curves of any flow control pulse, and is given by the as a recommendation by the manufacturer in the valve catalog. There you will find the graph to be somewhat like this. At higher values of delta P, if the valve is not pressure compensated, then what happens? Uh, One second. So at higher values of delta P, so this is the mathematical relationship, but at higher values of delta P, Q uh, it generally is it's seen that it falls like this. So that is due to the behavior of the flow control valve, that is the orifice section. Coming to the next question. A flow control valve having a flow coefficient, so it's a numerical CV, that is a flow coefficient. You should be aware of this particular coefficient. Like if it's discharge coefficient, then it's CD. That's different. So there you have to apply a different formula. And here it's told flow coefficient CV. So it is not dimensionless. It's having some unit. It is discharging hydraulic oil of specific gravity 0.9 hydraulic circuit at a flow rate of 60 lpm. What is the pressure drop across the valve? So it's a direct question. We know that Q is equal to CV into delta root over of delta P upon SG. So all the units are, you need to be careful about them. So as you can understand, the delta P will come as kilopascals here, and SG is unitless. The value 60 divided by 2.5. That's 24 square by 76. 518.4. Okay. So coming to the next part of the question. Coming to the next part of the question. After continuous operation, the hydraulic oil's density is reduced by 10%. So and that is practically possible because as the oil is continuously circulated, the temperature it increases because you are energizing the oil, right? So its internal energy increases and the temperature increases. As a result of that, the density may reduce. So here it is said that its density is reduced by 10%. So as a result, the SG will also be. So let me just write it as SG dash. That is the new SG. So that is reduced by 10%. So now your new SG is 90% of the old SG. That is 0.9 into 0.9. 0.81. So now what will be the pressure drop across the valve now if the flow rate is doubled? So your new flow rate, it's doubled. So 60 to 120. So from here you can again calculate delta P by using this same equation. CV is constant, so 2.5 multiplied by delta P. So they're asking you the new pressure drop divided by 0.81 equals 120. So delta P is how much? 120 by 2.5. 120 divided by 2.5. It's 48 square 0.81. So I'm getting 1866.24 kPa. So as you can understand that as we are increasing the flow rate, the delta P across the valve is also increased. Or we can interpret it in the other way around. If the delta P across the valve it's increasing by 4 times, say, then the value of Q will be increasing by 2 times. Yeah, it will be increasing by 2 times because we know that Q is directly proportional to square root of delta P. Okay. Coming to the next question, flow dividers are fluid power components having the following features. It can only maintain equal flow rates in the sub branches irrespective of pressure. Is it correct? It can maintain equal flow rates, but it only maintain equal flow rates? No. It can maintain flow rates at different proportions. It can be either 50 is to 50, that is like 50-50, or 75-25, or 60-40, depending on the design of the design and requirement of the particular flow divider. So this option is not correct. Had this only been not there, then it would be correct because it maintains the flow irrespective of whatever pressure is developing in the sub branches. And why the pressure develops? Due to resistance to flow. And where this resistance comes from? It comes from the load on the actuator. It can be used to split the flow in motor circuits. Yes, it can be used to split flow in the motor circuits. So suppose you have two different motors which needs to be rotated at the same speed irrespective of the load on the motor, such as in conveyor belts. So in such cases, you need to use such flow dividers. It can be used to synchronize the operations of two or more cylinders. Yes, if you want two cylinders to be operated at the same velocity, at the same stroke, then such type of to synchronize such operations, you can use flow dividers. So suppose you have two cylinders and it is pushing a particular gate, say. Now it may so happen that the load on this part of the gate is higher compared to this part. So in that case, if the load is not uniformly distributed on this entire plate, then it can so happen that if they were receiving flow independently, then this particular two cylinders may not extend uniformly. So that synchronization may not be there. But suppose we are sending them through a flow divider that divides it 50-50%. So whatever is supplied from the pump, that is divided in 50-50%. In that case, what will happen? They both will extend at the same velocity because equal flow is coming here. So what we know is velocity of the piston is nothing but flow upon area of the piston. If area of the piston is same, then since Q is so I am writing Q half because total Q is halved on in both the sub branches. So Vp is Q half by AP. Okay, so yeah, it can be used to synchronize the operations of two or more cylinders. Now, rotary flow dividers are pressure compensated. So first of all, you need to understand that what are rotary flow dividers. So flow dividers can be two types, like it can be like this spool type or pressure. This is pressure compensated because why we're coming to it, and this is the rotary type. So rotary flow means there will be two pumps which are connected by a common shaft. So what happens as this shaft is rotating at the same speed, therefore, and these pumps are positive displacement pumps. Okay, so they are positively displacing. Suppose from here Q is going, so they are positively displacing this much amount of uh, flow through this through the pump. So outlet 1 and outlet 2 are having the same flow rate at outlet 1 and outlet 2, since the shaft is rotating at the same speed, and hence uh, here we have, so whatever the load, whatever the delta P across this pump, that doesn't matter. It will positively send out this much amount of fluid. So we can't say that this is pressure compensated, because we are not using the pressure difference or the pressure differential across these two points to compensate this flow. It is due to the nature of the pump. Like we have positive displacement pump, and it will positively displace this much amount of liquid. Whereas on the other hand, if we are using this spool type design, then what happens? Suppose this is outlet 1, which is supplying to one actuator, and this is outlet 2, which is supplying to another actuator. So due to the load on actuator 1, the pressure developed here is P1, say, and due to the load on actuator 2, the pressure developed in the outlet 2 is P2. Suppose P1 is greater than P2, then what happens? This and this is the inlet, it is getting divided. So if P1 is more than P2, that therefore the back pressure, the liquid that is trying to flow out through outlet 1, that will be under higher pressure. So the pressure on this particular spool, which is freely floating here, this pressure, and here the pressure acting on the spool is P2 pressure. So since P1 is greater than P2, what will happen? By general intuition, you can say that the spool will be shifted towards the right. So what does that mean basically? If this shifts to the right, this particular flow, this particular throat or this particular port will get constricted. So what will happen? The Q will reduce, whereas this particular port will get dilated. Dilated means its area is increasing, so Q is increasing. So as we could understand that here, since the pressure was higher, pressure at this P1 pressure is higher. So originally, originally the flow through this would be like if there was no compensation, the flow would originally be restricted. Okay, so we don't want that. So that's why we are dilating this particular port. Like we are not dilating, it is happening due to this particular pressure differential P1 minus P2, and hence more flow is taking place through here, so that it can allow the this particular cylinder, wherever it is being used, or the motor, to operate uniform to this particular motor, that is second one, or the cylinder, whatever. So rotary flow dividers are not pressure compensated. Rather, this type of spool designs are pressure compensated. So this is also not the correct option. Priority flow dividers do not divide the flow into two fixed proportions. This is again true, because priority, by this name itself, you can understand that the flow dividers are not designed to divide the flow into equal halves, equal proportions. It should be it is designed to divide the flow so that one particular branch will be receiving the main flow, or a certain amount of flow, and once that is completed, the remaining amount is distributed to the other sub branches. So That is why we call it a priority flow divider. So it is again uh, correct option. Okay, so as I was saying that pressure compensation. So like how to like what is basically pressure compensation? Pressure compensation is when we talk about pressure compensated FC, flow control valves. What do we mean by that? So it means that the restriction or the cross sectional area through which the flow is taking place through the orifice, that will be um, you know that will be modulated, or that will be adjusted so that the flow remains constant. Okay, so yeah, we have it here. So let me discuss this question first. A needle valve has the following characteristics. It comprises an adjustable knob that raises or lowers the valve stem and the needle, thereby controlling the flow section. Yeah, this is correct because we have an adjustable. So this is the stem and this is the needle. So by rotating it, it can be lowered or it can be it can be lowered or it can be raised. And this particular section, it can be adjusted. So the flow through this will also be adjusted. It is bidirectional. No, it is not bidirectional because it generally sits on a knife edge, like this. So it generally sits on a particular knife edge. So that biases the flow. It gives a particular direction of flow. So it can either be from if this knife is edged like this, then the flow has to be from A to B. Like that's why for any needle valve, this particular direction is mentioned, the preferable flow direction. So this it is not bidirectional. Like you can't use it for this particular direction. Only one direction can be used. Discharge is inversely proportional to the square of fluid density. Discharge is inversely proportional to the square of fluid density. No, it is inversely proportional to the root over of fluid density. Right. So if we look at the formula for a needle valve, so as you can understand from here, again, see, this coefficient is not coefficient of uh, this is not this particular coefficient that we used. This is not a flow coefficient. It is a discharge coefficient. And we have the area here. And yeah, you can understand that Q is inversely proportional to the root over of fluid density, not square. So again, this is not correct option. This was correct. Discharge increases with throttle opening. Yes. As Q is increased, your discharge will increase. It can have fixed or adjustable orifice. Yes. So if you look at the symbol, this is for the fixed orifice type. This is for the adjustable orifice type. Okay. So draw the ISO symbols of the following: adjustable disc throttle type FCV. So for disc throttle, we use this particular symbol. The gap won't be this much. And this arrow shows that it is adjustable. Next, pressure and temperature compensated check choke valve. So you have a check valve that is FCV, you have a choke valve that is NRV, non-return valve. So this means that flow in one direction will be throttled. Throttle means it will be passing through the flow control valve. However, in the other direction, it won't be throttled. So, okay, next they are telling it is pressure and temperature compensated. As I was telling, what elaboration on the uh, pressure compensation or temperature compensation. So this symbol is for pressure compensation. This symbol is for temperature compensation. You can put this. These are the ISO symbols. Okay. Now let's talk about like why this is necessary. Why your pressure compensation is necessary. So generally, as we from this particular equation, if you see from this particular equation, um, when we reduce the cross section, say A, then your pressure is increasing. Okay, delta P. This is delta P. So when we are reducing the cross section, your pressure across this particular valve that is increasing. But what do we actually want? We are reducing this cross section to reduce Q, right? But what actually happens, like this is happening, but at the same time, the delta P is increasing. The pressure drop across the flow control valve, it is increasing. And as we know that Q is directly proportional to root over of delta P. So that's why Q also tends to increase. But what we actually wanted, we wanted Q to reduce. And that's why we reduce the uh, cross section, right? By using some sort of adjustments. Uh, so this is something undesirable. Now, like this change in delta P, that was unforeseen. Like we didn't anticipate that. Why that can come into picture? That can come into picture due to the dynamic loading conditions, where due to like when the load is changing on the actuator, the pressure is also changing. Okay, so I'm just writing like this. When the load is changing, the pressure is also changing. Pressure drop across this particular valve is also changing, and as a result of that, there can be some variation in Q. Okay, like whatever we want, this desired outcome may not be fulfilled due to the effect of this pressure changes in pressure. So again, due to change in Q, your the velocity of the piston may also vary, which is not desired or undesirable. Okay, you don't want the piston to extend at a variable speed. You want it to extend or retract at some constant speed. Otherwise, there will be vibrations and all coming into picture, and the desired operation may not be achieved. Okay. So that is why we want to use some sort of mechanism which will control this cross sectional opening based on the changes in pressure. Okay, if the pressure is varying, what do we want now? With changes in delta P, we want to change the area, or the opening through which it will the liquid will pass, or the fluid or the oil will pass. And this change should be such that your Q is kept constant. Q is maintained constant. Okay, as we could see that Q is dependent on both area and delta P. So if your delta P is increasing, your A should be proportionally reduced so that your Q is kept constant. Again, the other way around, if the delta P is reducing, the A should be proportionally increased so that Q is remained constant. And as a result of that, Vp should also be kept constant. Now there are multiple ways of doing that that has already been discussed in the video. One of the primary ways is just you are having two spools, like in a pressure compensated valve. What do you have? You have one main spool and one compensator spool. So the compensator spool is attached to a spring which is adjustable. I'm just representing it to this line diagram. This is not the correct symbol. This is the symbol. So what happens? This is the main spool, okay, and this is your compensator spool. What you are doing, you are tapping the pressures across the main spool. So if this was not pressure compensated, you wouldn't be having this thing. Okay. It would be like this. So now what you are having? You are having this. Okay. So if you see the delta P across the main spool, that is the pressure between these 2 points. So that is delta P. So what you are doing, you are tapping the one port and you are redirecting it to one end of this compensator spool. Similarly, you are tapping another from the downstream line and putting it on this part. These are basically ports that I am drawing, okay, or fluid lines. So now what happens? If this, so this is say P1, this is P2, and delta P is nothing but P1 minus P2. So if P1 delta P increases, that is the upstream pressure, it increases with respect to the downstream pressure. So if delta P increases, which means P1 is greater than P2, that means that it will push this particular spool against the spring towards this side, right? And as a result of that, what happens in this line? So here you have one opening. That opening gets shortened if this spool is moving this side. So if the spool is moving this side, what happens to A? It reduces. So what we saw here, as delta P increases, the compensator spool moves like this, and hence the area of cross section reduces. As the area reduces, now what will happen? The flow here will decrease, Q will decrease. As Q decreases, now the delta P will also reduce. Okay. Now as the delta P is reducing, again, like it is stabilizing the Q. It is getting stabilized. Okay. So this is how the pressure compensated, um, you know, flow control valve it operates. Okay, so coming to the next question, the role of pressure control valve is. So we already discussed about pressure control valve in the last session, I guess. So there are different types of pressure control valve like PRV, that is pressure relief valve, and pressure reducing valve, brake valve, sequence valve. So different types of valves are there based on like how, from where we are taking the from where we are reading the pressure. It can be from the upstream or the downstream, and whether it is normally open or normally closed. Based on that, we are using it in different applications. Okay. So the role of pressure control valve is to maintain the pressure level, to maintain force output of an actuator, to maintain the speed of the actuator, to maintain the torque output of the actuator, to responsible for the direction of the actuator. Direction of the actuator, we have direction control valve. So PRV is not, PCV is not responsible for this. Maintain torque output of the actuator. Yes, it by changing the pressure, by modulating the pressure level, we can change the torque of the uh, actuator. Basically, for the motor, speed of the actuator. For that, we have flow control valve. It can't maintain the speed of the actuator. However, by using brake valve, you can reduce the speed against the impacting loads. Like if you are having a very large load that is acting in the system and the actuator, and that is driving the actuator rather than the actuator driving the load. In that case, you can use um, this braking valve or brake valve. So okay, so those things are available. Um, so this is also not correct option. To maintain the force output of an actuator, yes, for um, hydraulic cylinders, it is the F. Uh, so as we control the pressure, we can maintain the we can control the force output, and it is also used to maintain the pressure level. We don't allow it to go beyond certain permissible limits that can cause damage to the hydraulic systems. Okay. Now we will be discussing two circuits. Like we already discussed about different type of valves. We need to see how this is being used to realize a particular operation in industry or uh, like in some mobile hydraulics. How what like we discussed about different type of valves and how that is being connected or interconnected so that it can carry out a given operation. So, to the first question, develop a pneumatic control circuit. You have to be careful about pneumatic or hydraulic, and depending on that, the valves will change. The symbol of the valves will change to implement the given control task. So, what is the task? A large bore double acting cylinder is to extend and clamp a workpiece when two push button valves are pressed simultaneously. For safety reasons, these push button valves are installed in such a way that both the valves cannot be operated with one hand. So they are independently operated, and both the hands must be used to operate these two valves. This is present in several applications where like for safety reasons, won't allow um, the cylinder to extend when you are when you are pressing the valve using one hand. Okay, so there are two different valves which needs to be independently activated at the same time, so that uh, the you are getting the final outcome, that is the cylinder is extending and clamping the workpiece. So as you can understand, we have two different valves which will be activated. So one second, showing lost your network connection. Thank you. Uh, okay, coming back to the question. Um, it is asking that there will be two valves that needs to be pressed independently at the same time, so that a particular cylinder is getting activated. It's pretty easy. So what, as it is said simultaneously, what should come to your mind? You should be using a type of valve that will allow the flow to happen only when like there is flow from both sides, like from both of its input sides. It's like AND gate. Okay. So let us try to draw the circuit. So starting from, so you can start from both sides. You can either start from the cylinder side or you can start from the valve. So there will be power source. There will be an FRL unit, that is the filter regulator and lubricator unit, since it's a pneumatic control circuit, and then that will be supplied to your regular circuit, right? So let's start. This is your filter regulator lubricator. Some problem with the stylus. Now you're doing what? You're bifurcating it into the two valves. So on one side, you have one push button actuator. It's a simple so I'm showing the activated condition when you are pressing both the valves. Okay, you can always show the other condition, that is when or it's better to show Okay, so let's show the condition when one of the valves is being activated, the other is not activated. So your cylinder is not extending. Okay, so let's show that condition. So suppose this is activated, so you have this particular configuration, and this one is not activated. Okay, so consequently you will be having this position. Now both this flow should be directed through the shuttle valve. Okay, so you can name this as P and D, like pressure and exhaust ports. Here also pressure and exhaust ports, and say 1.1, 2 and 1.4. Okay, and both of this will be giving a signal. So as you can understand, this one is logic 1, this one is logic 0, since there is no flow. So obviously we'll be having logic 0 here, since this acts as a AND gate. If either one is 0, it will be giving 0 output. So if both are 1, only then this will be 1, that is there will be flow through here. So this I am marking using red because this is not part of the circuit. Next, where will this go? This will go to your main DCV, because that DCV should also be taking care of your retracting stroke, right? So it has, say, two positions. One is this. So these are your A and B ports, say. And the other one will be P to B. Sorry. And say this is spring operated. So why I am placing this spring? It's showing that the cylinder is to retract when any one or both the push buttons are released. We will show how that operates. So here, this is my P button. Sorry, P port. These two are exhaust ports. Here, P is connected to B, and yeah, A is connected to exhaust port. So this is the retraction position. Why? Suppose this is your double acting cylinder. Double acting cylinder means on both sides of the piston you will be having ports. So this will be connected to A, and this will be connected to your B. Okay, you can put metering circuit here to control the flow, but the question hasn't asked about it, so you may not put it. Now tell me whether this is an extension position or it is a retraction condition. You can see that the air is flowing through here, then through here and here, here. So now here it is flowing through the P port, through here to here. Here air is not flowing through this particular valve, through the, like it is getting stuck here because this particular push button is not actuated. Okay. Hence there is no flow of air in this particular line. Then air is also flowing through this line. P to B and from here. So it is pushing the piston here, and the air on this side, it is flowing out through A to the exhaust line. It is going out through the exhaust line. So this is the retraction of the retraction stroke. Now suppose okay, now what? Now what we will do, we are pressing this to both of them together. Okay, so what I showed previously, same will happen if I am not pushing this one and I'm pushing this one, then this will get the flow, this will not get the flow. Okay, so both are same, so I am not drawing it again. But let's see this particular operation when both are pushed together. Okay, so what will happen now, this particular position will get activated. So here is the line, and same on this side also. Now from both 1 2 and 1 4 you have fluid power, that is the air is coming in. So this particular shuttle valve, it is both 1 and 1, it acts like AND gate as I said, so the output will also be 1, that is the flow will take place now, right? So now what will happen, this particular cylinder position will get activated, right? So I have to change, so your pressure port, so your this is your pressure port, and pressure port is connected to A and B port is connected to exhaust port. There are two different exhaust ports for A and B lines in this direction control valve, as you can remember. And this is connected to A, this is connected to B. Now what happens? Now if you see the main flow line that is taking place here, it will go through this to A and the cylinder will extend now. Now the cylinder will extend. So now what happens when both the pistons are when both these two valves are operated or they're pressed. If one of them are released, then immediately the flow to this 1 4 or 1 2 will get choked or will get like there will be no flow, and no flow will be coming to here due to the spring return. This particular position will be assumed and the cylinder will immediately retract back. So the given operation is realized here. there can be some typical examples of the previous application in industry. Suppose you are punching something. So there are two valves. One is foot operated, one is hand operated. So while you are pressing the foot, one the like it is not punching. Okay, so as soon as you are pressing your hand while your foot is also pressed, the cylinder will come and punch, and as you're releasing your hand while keeping your foot intact on the valve, then immediately the cylinder will retract again. You bring the next workpiece using a sequence valve. You can do that, like you can automate it by using a sequence valve, or you can also do it manually depending on what type of operation you are using. So then again you are pressing using your hand, and it will come and punch. Okay, so this type of operations are pretty much frequently seen in industries. Coming to the next circuit, develop again a pneumatic control circuit to implement the given control task. A large bore DAC double acting cylinder is to extend and punch a workpiece when either a push button valve or a foot pedal valve is pressed. This is just the opposite of what we discussed in the previous question. So this is like there will be two remote control valves, say remotely operated valves. So both the operators can actuate the cylinder. So the operator who is sitting with the control of one valve can also actuate the cylinder, while another operator can also actuate it. So these things are also visible in various industrial applications. The cylinder is to retract when a second push button is pressed. So these things need to be kept in mind while you are designing. Okay, let's try to look at it. So as you can understand, or here also you have to use the particular type of valve. Just give me a second. Okay, so let's start again from the power pack. So instead of drawing this entire thing, you can draw a simple triangle like this. So this is equivalent to this entire thing. Okay. Now let's for this one, I will just draw a triangle. So there are two valves, as it is told, for actuating a particular cylinder, and there is another third valve for retraction of the cylinder. So I'm using simple valves. This is hand operated. While it is foot operated, it should be a pedal, foot pedal type, right? So I am showing extension operation only here, not retraction. Okay. So either of these two valves needs to be on. Like I mean, it needs to um, allow flow to the cylinder. So let's consider that now the push button valve is pressed, while the foot operated valve is not pressed. So this one is pressed. So this will receive flow. I am drawing this triangle again. I already discussed this triangle replaces the power pack, and your like the basic compressor unit and the FRL unit. And here this is not pressed, so this particular null position is activated. So from here, as you can understand, flow will come, and from here there will be no flow. Now you should be using a type of valve that will allow the flow if any one of this is 1. So it is AND type of valve. So this shuttle valve, I guess this is called shuttle valve. Okay. So you are having 1. So in either one of this is pressed, the ball will be directed towards the opposite. Like this is basically an NRV. So that ball will move to the opposite end and it will sit there. If both are pressed, then also this will be 1. Okay. So now it is going to the main valve that will operate our cylinder. Now you have said that for the retraction stroke, there is a second push button. Okay. So this is your second push button. This was the first one. As I said, this is extension stroke which is running. So retraction should be in the null position at that time. So this is, you should label all these positions. P, E, P, E, P, E. So we are using, sorry, this will be dotted. Why? Because there is no pressurized flow. So P2A, P2E. Is again connected to the power source. What is the other position that is not activated here? So let us name this power symbols as like power signals as 1 4 and 1 2, and here say okay. So actually no, these are the nomenclature is also like tricky, like you can't just randomly name them. So generally if we name them, it should be based on the ports that it is connecting. Okay. So let me just rub this one to avoid confusion. So suppose this P port is your 1 port, and B and A are basically 2 and 4, and the 3 and 5 are the 2 exhaust ports. So if your 1 is connected to 4, then this signal is basically 1 4. Whereas if your 1 and if the pressure port is connected to B, like in this case, like A is connected to E and P is connected to B, in that case it is basically 1 2. Okay. So in this case 1 4 is activated, so I am showing this one only. So as you can understand that if we are writing these names, sorry, if you are writing this signals as 1 2 1 4, then you should name the ports as 1 2 3 4 5 rather than A B PE ports. Okay. Next you have your double acting cylinder. Okay. and this is the extension stroke. This is the retraction link. I hope I didn't miss out on anything. Yeah. Okay, one more thing. In the question, they have said large bore double acting cylinder. Okay, so generally for a large bore, you should be using a meter out or meter in circuit. Because the flow should be controlled, right? So that's why it's advisable that you use a meter out circuit. So like it can be meter in or meter out, anything. Like here, let's say we are using meter in circuit only. What will happen if the flow is happening from this direction during the retraction? It will happen slowly. During extension, sorry, the retraction will be fast. I'm sorry, the retraction will be fast because it will be passing through this NRV. Whereas the extension, since it's a large bore double acting cylinder, it is designed to carry heavy loads. The load should be shifted very slowly in a controlled manner, and that's why at that point, what will happen? The flow should be metered. It should flow through this orifice so that it extends slowly. Here also same thing. It was a double acting large bore double acting cylinder, so your extension should be slow. So here you can use a meter in circuit at your convenience. So what will you do? You will put a flow control valve here and a NRV here. So NRV, since it's a meter in, so the it should be like this. So when your flow is happening from this direction, it should flow through this particular flow control valve only. Okay. So yeah, your extension is controlled by the flow control valve. Here also extension is controlled. Okay, so with that we come to the end of this particular session. If you are having any doubts, please you can address them now. Yeah, okay, so do you have any doubts related to today's session, or like any general query regarding valves, flow control valves, traction control valves, or pressure control valves? With this session, we are coming to an end to the valves chapter. There are other different applications also. I would request you to go through some standard textbooks and solve this type of questions where see in the lecture videos you can see one particular application of a particular valve, say um, your pressure control valve, some sequencing operation is there. Okay, so only one application you are seeing there, but if you are not seeing the examples or some other problems, if you're not attempting them, then you won't be able to, by seeing the question, you won't be able to judge like which type of valve you must be using. So such things will come with practice. So I will request you to go through some standard textbooks for this circuits part, along with the examples that we are solving in class or sir has discussed in the lecture videos. Okay, so any more doubts or anything, any questions pertaining to bugs, since we are discussing that section today? If not, we can close the session. Yeah. Shall we close the session then?